In the last lecture, we introduced a genie-assisted version of the Thompson sampling algorithm, in which a genie told us the reward parameter on the best arm. We started the analysis of this algorithm, and we are going to continue with it this time. So let me share my screen. Okay, so let me very briefly remind you of the algorithm and some of the notation. The setting we have is that of bandit with two independent Bernoulli arms. The success probabilities are mu1 and mu2. We assume that mu1 is bigger, and delta denotes the difference mu1 minus mu2. So we want to analyze the regret up to some arbitrary time horizon capital T. In order to do that, we introduce this quantity L, which is defined in this way. So it's 2 log T over delta squared rounded up to the nearest integer. And we define tau to be the smallest time up to capital T that the suboptimal arm 2 has been played at least L times. The idea is that L has been chosen sufficiently large that if arm 2 has been played L times, then we should have a good enough estimate of the true reward parameter mu2 on this arm, good enough for the time horizon T. Okay, so that's the intuition behind the choice of L and the definition of tau. Lemma 2 says that because L is large enough, and so there's a good chance that we have a good estimate of mu2, it's unlikely that a sample drawn from this distribution will exceed mu1. Okay, mu2 is smaller than mu1. So the prior for mu2 concentrates around in the vicinity of mu2. Mu1 is known exactly. So we need, in order to play arm 2, we need a sample which lies far in the tail of this posterior distribution, and that's an unlikely event. Its probability is bounded by 2 over T. This is how unlikely it is. Okay, so this is the assertion of lemma 2. And then last time we showed that taking this lemma for granted, that the regret up to time T is then bounded by this gap delta between the reward parameters times L plus 2, which is essentially L. So if you multiply this out, we get a 2 log T over delta regret bound. Okay. Okay, so we still have to prove lemma 2, and that's what we are going to do this time. Okay, so let's define these two events. A sub T is going to define the event that theta 2 is at least as big as mu1. This is the event we are interested in, that our sample from the posterior distribution for mu2 exceeds mu1. BT is an auxiliary event we define. So this is the event that the expected fraction of success is in the first N2T place of arm 2 is not much, is not much bigger than its true value. So as N2T gets large, this ratio should converge to mu2. And BT says it's not too much bigger than that. It's at most mu2 plus delta over 2. Okay, so for large values of N2T, the event BT should have probability close to 1 intuitively, and BT complement should have very small probability. And the reason for defining this event BT is the parameters of the random variable theta2 is drawn from a beta distribution, and the parameters of that beta distribution are given by in terms of S2t and N2t. And so they will play a role in bounding the probability of AT. Okay, so if t is bigger than tau, then by definition of tau, arm2 has been played at least L times. So we can bound the probability of BT complement. BT complement is the event that S2 is the event that the empirical fraction of successes in the first N2 trials is bigger than mu2 plus delta. So that it's the event that it's much bigger than its mean. The sample mean is much bigger than the true mean. And these are sums of Bernoulli random variables. So these are sums of random variables restricted to the interval not 1, and hence we can apply Hoeffding's inequality to this event. So the probability of BT complement is the probability that just look up Hoeffding's inequality. So this probability is bounded above by e to the minus twice the number of trials times the square of the deviation from the true mean. So delta over 2 is the deviation from the true mean, and so we get delta squared over 4 here. And as we saw, N2t is bigger or equal to L, and we have a negative exponent here. So this is bounded in turn by e to the minus delta squared L over 2. And if we look at the definition of L here, so delta squared L gives us a 2 log t, and dividing it by 2 gives us a log t. Okay, so delta squared L over 2 is basically log t. And e to the minus log t, e to the log t is t, so e to the minus log t is 1 over t. So that's our bound on the probability of the complement of the event BT. Okay, so how does that help us? What we are interested in is the event AT, and we'll bound this as follows. So AT is the union of the mutually exclusive events AT intersection BT and AT intersection BT complement. So the probability of AT is the sum of the probabilities of these disjoint events whose union is AT. And now we can rewrite each of these intersections in terms of conditional probabilities. So the intersection of AT and BT has probability BAT given BT times PBT, and similarly here. And now we are going to use the fact that all probabilities are bounded by 1. So the probability of BT is at most 1. So the first term in the sum is at most this conditional probability. And here the conditional probability is at most 1. So the second term is at most the probability of BT complement. Okay. So we bound the probability of AT as the sum of these two terms. We've already bounded the second term in the sum. We have this upper bound 1 over t on the probability of BT complement. So all that remains for us to do is to obtain a bound on this conditional probability of AT given BT. And that's what we are going to do in the rest of this lecture. Okay, so let me remind you, by conditioning on BT, we are saying that the number of successes observed in N2t place of the second arm is not much bigger than its true value, mu2 times N2t. Okay, so we don't observe an unusually high frequency of successes on arm 2. That's the event BT. Now, AT is the probability that when we draw from the posterior distribution for this arm, we don't get a value bigger than mu1. So there are two ways this could happen. This could happen because we observed an unusually high frequency of successes, and therefore the posterior itself is shifted away from the true mean. And by conditioning on BT, we are excluding that possibility. And we are saying the posterior is concentrated not too far from its true mean. And so the sample is picking something out in the tail of the posterior. So the only way AT can happen if we condition on BT is that when sampling from the posterior, we see something unusually far in the tail. And we want to bound the probability of that event. Okay, so that's what we are going to do next. Okay, so θ2 at time t plus 1 is sampled from the posterior distribution for mu2 after t rounds, and that's a beta distribution with these parameters, 1 plus S2t and 1 plus N2t minus S2t. So the number of successes plus 1, the number of failures plus 1. Okay, so now we want to say something about the probability that this beta random variable is bigger than mu1. And this is a beta random variable with integer parameters. And we are going to use lemma 1, which related beta distributions to binomial distributions. So the probability that this beta random variable is bigger than mu1, and I've made this conditioning explicit. So the parameters of the beta depend on S2t and N2t. So it's after conditioning on these that you get a beta. Okay, and we are interested in the probability that this sample is bigger than mu1. And that's exactly the same as the probability that a binomial distribution with parameters, which is the number of trials in the binomial is the sum of these two parameters plus 1, and that's what we have here. And the success probability is this quantity mu1 that we are interested in. And then the event, the probability the beta exceeds mu1 is the probability that the binomial is smaller than S2, smaller or equal to S2. This is what lemma 1 gave us. So I'm just spelling it out. Okay, so we've expressed the event we are interested in, which involve beta distributions, in terms of an event involving binomial distributions, and we know how to get tail bounds on binomial distributions via Hufting's inequality. Okay, and let's just check that we are in the setting where we can apply Hufting's inequality. So N2 is the number of trials in this binomial, mu1 is the probability of success. So the expected number of, so let me get rid of this. So N2 is the now N2 plus 1. Okay, we can bound this by the same thing for binomial N2 mu1. So N2 is the number of trials, mu1 is the probability of success. So the expected number of successes is mu1 times N2t. And we've picked S2t to be smaller than mu2 plus delta over 2 times N2t. And mu2 plus delta over 2 is itself smaller than mu1. So S2t is definitely smaller than mu1 times N2t. So we are asking for the probability of an event that a binomial random variable is smaller than its mean value. And the probability of that event can be bounded using Hufting's inequality. So in this setting, if S2t is smaller than mu1 N2t, then we can say that this binomial being smaller than its mean is bounded by e to the minus 2 times the number of trials times the deviation from the mean squared. So we want a deviation from the true mean is mu1. We are asking that the binomial take a value smaller than S2. And so we are asking that the sample mean deviate from the true mean by at least this amount, and we are squaring that. So this is just Hoeffding's inequality. And if we condition on the event Bt, then S2t is smaller than this. And by definition of delta, mu2 plus delta over 2 is the same as mu1 minus delta over 2. So we've just substituted here. And so the difference mu1 minus S2t over N2t is at least delta over 2 here. And so what we get is that the conditional probability of AT given N2t and Bt is at most e to the minus 2 N2t times this difference is at least delta over 2. So we get delta squared over 4. Okay, that's just calculation. Okay, so we have a bound on the conditional probability of AT given Bt and N2t. Now, how big is, and we only want to bound this conditional probability for t bigger than tau. And if t is bigger than tau, what can we say about N2t? It's at least as big as L. That's the definition of tau. So by definition of tau, N2t is at least as big as L. And so we conclude that this conditional probability of AT given Bt is at least e to the minus L times delta squared over 2. And L was 2 log t over delta squared. So when you multiply this out, you get e to the minus log t, which is 1 over t. So the conditional probability of AT given Bt is at most 1 over t. We also showed that the probability of Bt complement is at most 1 over t. And combining this, we get the upper bound that the probability of AT is at most the sum of 1 over t and 1 over t, which is 2 over t. And this is what the lemma stated. So we have proved the lemma, which said that the probability of the event of interest AT is at most 2 over t. Okay, and then we also proved the corollary earlier, but just to repeat, the regret of delta is incurred every time that arm 2 is played. And so the total regret up to time capital T is delta times the expected number of plays of arm 2. And as we saw, lemma 2 says that the probability of arm 2 being played at any time after tau is at most 2 over t. That's what we proved. So adding up 2 over t, t times or t minus tau times the number of plays of this arm after time t is at most 2. And if tau has not even occurred up to time t, then of course this is 0. Okay, so the upper bound of 2 still holds. And by definition of tau, the number of times the suboptimal arm is played up to time tau is at most L. So the total that it's played up to time t is L plus 2 at most in expectation. Okay, it's played at most L plus 2 times, incurring a regret of delta each time. So the total regret is the product of these things. And if you substitute, you get this upper bound on the total regret. The 3 here comes from the fact that by rounding up an fractional value to an integer, we have added at most 1 to that fraction. Okay, so that completes the proof of the lemma and of the corollary. And so let me conclude with a few remarks. So we presented the Thompson sampling algorithm. We wanted to analyze the regret of this algorithm, but we said this is too difficult because the choice of which arm to play depends on the posterior distributions, which depends on past choices of these arms. And so there's a complicated dependence on history. And to simplify the analysis, okay, so what is the main difficulty in the analysis? So we got a simplified version where we only wanted to bound the number of times a suboptimal arm is played. And that's relatively easier to do because we condition on if for whatever reason to do with history, the suboptimal arm is not played many times, we are fine. Very little regret is incurred. If it's played many times, then because it's played many times, we learn more and more about the true parameter of this arm. And since it's suboptimal, once we've learned it well enough, we are not going to play it. So we can say, so we picked a parameter. In our case, it was 2 log t over delta squared. And we said we don't know how long it will take for the algorithm to play it this many times. Maybe it's played very quickly, maybe it takes a long time. We don't care. But after it's played this many times, we get a tight bound on how many further times it's played. So that's what we did. So there was this initial number of plays about which we could say we don't care how long it takes to do that. But for the optimal arm, we can't take a similar approach because let's say we play the best arm a certain number of times and we just happen to be unlucky and see an unusual run of failures when playing that arm. Then the effect of that bad luck can stay with us for a long time because by playing this arm too few times, you don't have a good estimate of its true parameter. So you think it's bad, and so you don't play that arm. So it takes you a long time to correct this misperception, and that's the difficulty when in not knowing the parameter for arm one. We sidestep this by having a genie tell us the true value of the best arm. And if we do that, then we don't have to worry about the situation. And so it becomes much easier to analyze. Okay, I think I've just written out what I just said. Okay, so that's why we had to invoke a genie to simplify the analysis of the algorithm. Okay, so that concludes our analysis of a simplified version of Thompson sampling, which is the only version we are going to study. And so it concludes our discussion of the Thompson sampling algorithm. We've only stated the algorithm for 2 Bernoulli arms. Generalizing to any number of Bernoulli arms is completely straightforward. The statement of the algorithm is obvious. The analysis of the genie-assisted algorithm is exactly the same. So long as the genie tells us about the best arm, the same bounds apply to each of the suboptimal arms. So you just have to multiply the bound we got by the number of suboptimal arms. Okay, what about other reward distributions? If a conjugate prior is known for those reward distributions, then the statement of the algorithm is again quite straightforward. It can be implemented. The analysis could be harder, so we won't say anything about the analysis for the general setting. But at least the algorithm itself can be defined for a wide class of distributions for which conjugate priors are known. and then it's computationally easy to implement. The algorithm can be stated even if there are no conjugate priors known. It just becomes computationally very difficult to implement as the number of observations increases. Okay, so those are some concluding remarks, and we stop this lecture here. And this is the last lecture in the first half of this unit. So I'll stop